Hello, everyone, and welcome. I'll be talking about the weight of the robot. I will divide this up into several parts, and this is part one. All right, so anyway, this is in Keyshot. This is dolphins at this place. I don't know where that is. It's the Bing screensaver. So I try to put this in my videos. I always try to put something a little bit funny in my videos to start them. This is a mannequin that I created. It's the same size and proportions as a human being. And I use it in my videos sometimes to show proportion of what I'm drawing would look like compared to a human. And the mannequins are kind of playing jokes. I was talking about the robot walking along, so they made little stilts and strapped the stilts onto their feet, and they're walking around on the stilts. And I just thought that was funny. Why not? I do like to put in anything that I'm doing the fact or the statement that anything real could hurt somebody. And so if you have something real, you should manage it. My advice is manage it in a manner that is legally allowed and reasonable and safe. And if you can't manage it in that manner, then my advice is do not create it as a physically real item, because particularly these robots and these limbs and the hydraulic cylinders, that could do a significant pinch on somebody and actually hurt them badly. So it shouldn't be done by people that are not careful and don't know what they're doing. I do have a website, Pistonrobot, and the arms and legs and robot, they're in this part of the menu. And I did a discussion about a hand for a robot and a discussion about the robot walking along with these hydraulic cylinders. And that's what I'm going to talk to you about. And I would say, again, the hydraulic cylinders in robots, there is just a general conclusion among the robot people that the hydraulic cylinders are not going to work. It will fail. And I think they have the opinion it will fail based on hydraulic cylinder work that was done a long time ago. And they also don't realize that the electric motor gearhead system that they have is not going to allow them to make a robot that truly can mimic a human being. That electric motor gearhead system doesn't have enough strength. And so we'll talk about that for a second. And these are all, some of these drawings are in SketchUp and some of them are in Keyshot. I use SketchUp to create my drawings. I use Keyshot to render them because they're so pretty in Keyshot. And we'll talk about that. All right, and this is just the lower leg of the robot, the left foot. Okay, and I gave the robot a big toe, a little toe, and a heel. And the mechanical structures that run the toes are the same. This pad for the big toe, I made it bigger because in human beings, the big toe is bigger. I don't know why it's bigger, but it is. So I made it, this is the only thing that's bigger. The rest of it is the same. And the toes can flex up and down. And the toes have in them a dual action, a parallelogram type structure where now in a lot of my drawings, I lower the opacity of the material so you can see what's going on in there. And I also add all these different colors so you can see what's going on. The truth of the real robot, it's all going to be this color. It's just going to be metal. But this hydraulic cylinder has two springs in there, and it acts sort of like a shock absorber, and you can also control how fast the fluid flows from one side to the other side, so it acts like a shock absorber. This one you can actually send fluid to under pressure and adjust the position of the toe. And what this does is allows the toes to act as shock absorbers, and it allows the robot to know where its feet are and where are the forces on the robot by measuring the forces in these toes. And this is the ankle of the robot. And in human beings, they can move their foot where the toes go up and the heel goes down, or the heel goes up and the toes go down. And so that motion is dorsiflexion and plantar flexion. So that is one motion that a human foot can have. The other motion that a human foot can have, this is on the left side. So this is the left toe going up, and the right and the left big toe going up, and the left little toe going down. So it rotates this way. And that's called eversion of the foot when the big toe goes up. You can also have the big toe go down and the little toe go up, and that's inversion of the foot. So the human foot can move around two different axes. And the way that human beings are put together is that the muscles work against leverage, and the calf muscles, the leverage is about 3-to-1. So if this hydraulic cylinder, which is the calf muscle, this hydraulic cylinder controls eversion and inversion, this hydraulic cylinder controls dorsiflexion and plantar flexion. It's about a 3-to-1 ratio. So if this moves 1 centimeter, it actually moves the foot by 3 centimeters. And the reason this is important is if you have a 200-pound robot and you want it to stand on its left foot, just on its left foot, and then you want it to lift its heel up in the air, if the robot weighs 200 pounds and there's a 3-to-1 leverage, then this device has to create a force of 600 pounds. In human beings, the maximum rate of contraction of a human muscle is 15 centimeters per second. And it can go from not moving at all to maximum movement rate in 150 milliseconds. This means that in order for this to be a human mimicking foot, this device has to go from not moving to 15 centimeters per second in 150 milliseconds, creating 600 pounds of force. And, okay, so there's 3 things that control the device that runs the motion of a human mimicking robot. One is how much force does it need to make? The second thing is how fast does it need to move that force? But the third thing is the form factor. And in actual human mimicking robots, it's not good enough to satisfy one of these. You have to satisfy all 3. Amount of force, speed of force, form factor. The form factor for this calf muscle in this robot is 2 inches in diameter by 4 inches long. So you have to have a structure 2 inches in diameter, 4 inches long, that can create 600 pounds of force in less than 150 milliseconds and move it at 15 centimeters per second. And if you don't have that, then you don't have a human mimicking robot. And what the electric motor robot people, I don't know if they haven't realized it or they just don't want to talk about it. But for this to be electric, you would have to have an electric motor that's 2 inches in diameter and 2 inches long, connected to a gearhead that's 2 inches in diameter and 2 inches long. And this electric motor system is going to create 600 pounds of force at 15 centimeters per second in less than 150 milliseconds. And here's the actual truth. There is no electric motor that can do that. I don't think, using the laws of physics, I don't think it's even possible. And it has to be this small because the legs of a human mimicking robot are not, they can't be just arbitrarily. You can't have something down here the size of a football because the two legs would run into each other. And a hydraulic cylinder can do that. This is nothing for a hydraulic cylinder. It's just simply not a problem. And so this is the point that I'm working to demonstrate. And the robot people have no interest in it at all. I think they think it's not wrong, it's impossible, and there's no need to talk about it. And so I need to demonstrate it. And what I need is to create some parts that allow me to demonstrate that. And you know, I don't have funding because nobody thinks this is right. So I have to do this with my own funds. And so it can't be too expensive. So that's what we're working on. And the next thing we need to talk about is hydraulic cylinders. So the hydraulic cylinder for the mechanical engineering people, here is the big calf muscle of the piston robot. The hydraulic cylinder has a connection point on one end of it, an end cap on one end of it, a hydraulic cylinder. The other end cap has a hole in it so that the piston rod can come out. Inside the cylinder is the piston head, and there's a connection on the end of the piston rod. So the hydraulic cylinder is this plus this plus this plus this plus this plus this plus this. That's a hydraulic cylinder. I think if you showed this structure to most human beings that are not mechanical engineers, they would say that's a piston. And so because of that, I named my robot Pistonrobot, because that's a kind of a cool name, and I think that's what people think the robot is. And this is showing the structure of the knee. And one of the things that's important with a human mimicking robot is that it's called range of motion. It's how far can this go that way? In human beings, this can go this way to right there. You can't extend your knee any further than the long axis of your thigh, but you can bring it down to 90 degrees, but you can actually bring it back up. You can take this heel and just about touch that. And the reason I'm mentioning that is in order to get that range of motion for a human mimicking robot, I found that 2 hydraulic cylinders is a better deal than doing one. It's very hard to get a joint to move beyond 90 degrees with just 1 hydraulic cylinder. All right. When we talk about a robot under the control of, an autonomous human mimicking robot, and we'll go look at the robot. I'll show you some other drawings. This is what I was demonstrating, or going to demonstrate about. I did a robot hand. Of note, sorry, I got it backwards. When the big toe is up and the little toe is down, that is inversion of the foot. And when the little toe is up and the big toe is down, that is eversion of the foot. And she is taking her foot and pointing it at the clock, which means I'm out of time. So I'll stop here and we'll restart as part 2.